Thank you. Okay. Well, for those watching at home, they they missed us taking the derivative of the Gaussian distribution. So, I mean, I will do a 1 second review of that after hiding this. Uh, what we just did was finding the derivative of e to the minus ax squared using the chain rule. So as we saw, the chain rule says to take the derivative of the outside function, e to the x, which is itself e to the x, leaving the inside function left alone, and then multiplying by the derivative of the inside function, which here by the power rule is minus 2ax. So we found the overall derivative is minus 2ax e to the minus ax squared, and then I ranted a little bit about how this occurs in quantum mechanics. But good. Anyway, there we go. Back to the task at hand now that we are recording. Thank you for that. Alright, what should I do to differentiate these bad boys? Caution cinch.
Should we start by distributing?
Yeah, I mean, you could do that. If you prefer, we could write this as a half e to the x plus a half e to the minus x, and same thing here. I guess, yeah, half e to the x minus a half e to the minus x. Good. Okay, so now derivative is linear, so we could just differentiate each of those terms, and when I do that, what do I get for, say, the derivative of cosh?
In deep thinking, I believe that derivative is... I feel like I might be applying the derivative of e to the x wrong here, but I feel like our first one is going to be 1/2 e to the x plus, let me think. Are we going to need the chain rule here?
Yes, because there's a minus sign upstairs in the exponent. Good. So what does the chain rule tell us?
So we're going to start by putting down the 1/2 for everything, left parenthesis, that stuff.
Okay, sure. So then what's the derivative of e to the minus x, the second term then, inside the parentheses?
So I believe that this is going to be e to the x. Is that correct? E to the x times -1?
So it should be e to the minus x times minus 1.
Right.
Derivative of the outside with the inside left alone, so you don't change the exponent. So indeed, this is 1/2 e to the x minus e to the minus x, which is sinh. So the derivative of cosh is sinh. Notice this is different from the ordinary trig functions. When we took the derivative of cosine, it was minus sign. But in the hyperbolic case, the derivative of the hyperbolic cosine is plus the hyperbolic sign. Good, okay. Same thing, same strategy, I guess. What happens when we differentiate sinh?
So we are going to have 1/2 left parenthesis e to the x, let me think, minus, this is the same thing as before, minus, wait, no, this would be plus e to the -x.
Yes, good. Just by the chain rule, we have an additional minus sign due to the inside function being minus x, but that overall minus, or that additional minus cancels the overall minus to give a plus. I agree. So, by definition, this is cosh x. So, the hyperbolic functions have no relative minus when you take derivatives. The derivative of cosh is sinh, the derivative of sinh is cosh. You don't get any minus signs. Different from the ordinary trig functions. Good, okay. Questions on these guys?
I have no questions.
Okay, good. Good for warm-up. Alright. This is, I think, mostly exactly what you said. Taking the derivative term by term, pull down a minus sign, you get the sinh, pull down a minus here, cancels to get a plus, you get the cosh. Okay, so now I owe you a proof of the chain rule. This is a bit involved. So let's first remember the statement of the chain rule, and then I'll prove it. So the statement of the chain rule is that if we assume that we have two functions f and g, g is differentiable at a point a, so g is going to be the inside function, right? We're thinking about f of g of x. So the inside function has to be differentiable at a, and the outside function f needs to be differentiable at g of a, because g of a is going to be what gets plugged into f, so this is differentiable at g of a. So we have these two differentiability assumptions. The conclusion of the theorem is that the composite, f composite g, is differentiable at a, and the derivative, f composite g prime at a, is f prime of g of a times g prime of a. Okay, the proof is hard. This one requires some creativity. If I didn't just look up the proof of this in Spivak, it probably would have taken me, a couple days thinking to figure it out. So let's see why it's hard. So to prove that a derivative exists, as usual, we have to use the definition. So this is the definition of the derivative f composite g prime at a. It's the limit as h goes to 0 of f of g of a plus h, because the inside function g is the one that we're plugging in this a plus h into. So f of g of a plus h minus f of g of a over h, and this is what we want to prove. We want to prove that this is what the chain rule tells us, f prime of g of a times g prime of a. So the trick is going to be to try to split this difference quotient that we're trying to prove the equality of. We're going to try to split this into a product of two functions. So roughly we're going to try to pick a function which I call phi, the Greek letter phi. We're going to put inside the limit a function phi whose limit at 0 we want to be this first factor, f prime of g of a. And then this thing we're going to try to massage to look like the difference quotient that defines the derivative of g. Right? So inside the limit we want this thing which defines the derivative of g. So if we can do that and make all of the details work, then taking the product of those limits will prove the chain rule. So let's make that a little more explicit. What do we have to do? We're going to define that function phi of h. We want phi at 0 to be f prime of g of a, as I've said, because that's the first factor in the thing we want this to be equal to. And we're going to try to show that we can take this limit, split it into a product inside the limit of these two factors, and then if we prove phi is continuous, this is going to be a big step. We're going to have to prove phi is continuous, then we're allowed to split this into two limits. Because if phi is continuous, both limits exist, and we've proven you can split a product of limits into the limit of the product when both of them exist. So I've already answered one of the questions actually that I wrote for you here. What properties must phi of h have? One, it must be continuous. Two, we need phi at 0 to be this first factor, f prime of g of a appearing in the chain rule. And I'll ask you to do a little algebra. So what should phi be equal to away from 0? So if I'm going to match up the left and right side of this first line of the equation inside the limit, which means h not equals to 0, let me just write out the left and right side. I'm trying to match up f of g of a plus h minus f of g of a, all, did I do this right? Yeah, one more parenthesis here, all over h. That's inside the limit on the left side. I'm trying to match that up to the product phi of h times g of a plus h minus g of a over h. So I'll ask you to do the algebra. What should phi be inside the limit? So when h is not equal to 0, what should phi of h be in here if I want this equation to be true?
This is probably wrong, but I would say the inverse of f.
The inverse of f. So do you mean the multiplicative inverse like 1 over f, or the actual inverse function?
The inverse function.
Why is that true again?
I don't know.
Okay, so maybe we could just do algebra here if we're setting the top equal to this. So why don't we cancel h's since we're assuming h equals 0 and then solve for phi. So what does that give us?
Wait, is it going to be 1 over h, or am I missing something?
Well, no, when we cancel the h's, right, we have phi times the quantity g of a plus h minus g of a equals f of g of a plus h minus f of g of a. So I'm just suggesting divide both sides by this, and then write phi of h equals f of g of a plus h minus f of g of a, all divided by this thing, g of a plus h minus g of a. It's just algebra. It's phi times this thing equals this thing, so I say divide both sides by this, right? I sense confusion. Is this...
I understand it fine. I just didn't think that you could be that. What's proper? Trying to think of the adjective for this.
Cavalier, flippant. I don't know which.
Yeah.
Yeah, good. So, well, I mean, this step was just algebraic, but yeah, in general, one should try to reason from first principles rather than just guessing. I feel like the F inverse was just a wild guess, but try to know why you're guessing things if you guess things.
Oh, I wanted to undo the F somehow.
So that would make sense if this were composed, if it were phi of f, right? Then you would say, yeah, phi should be f inverse to undo the phi. But this is just multiplication. This is not function composition, right? Nowhere are we composing phi with f. Right? This is all just multiplication.
Okay.
Good. Okay, other questions on what we've done in this slide? I feel like it's not totally clear, but maybe it will become more clear as we go on. But preferably if questions, ask them.
I do not have any questions.
Okie dokie. Alright, let's go onward then. So as we saw...
Wait, that wasn't the proof.
No, that was the plan for the proof. We didn't prove anything, right? We were just planning what we're going to do. As we say, we have to prove phi is continuous. We have to actually do the calculation. So this was just the exploration, so to say, right?
Okay.
Alright, so as we saw in the exploration, we wanted to find a function phi, and we want it to be, this was the algebra we just did a moment ago, so we want phi to be equal to this quotient whenever the denominator is non-zero. So we can only define this quotient when g of a plus h is not equal to g of a, because if they were equal, the denominator would be 0. So this was the first condition we want phi to satisfy. The second was that we wanted phi of 0 to be this product f prime, or sorry, this composite f prime of g of a, which appears in the chain rule, because that's the thing that we're trying to prove this limit is equal to. So we have these two conditions we want to impose on phi, so we define it piecewise, and then, as I pointed out in the previous slide, then we have this just by algebra, that the difference quotient that we're studying is given by the product of phi and this simpler difference quotient involving g. So that was the algebra that we just did. And notice that this equation is true even if g of a plus h equals g of a, because then the right side is 0. Since this is 0, phi is f prime of g of a, and the left side is 0, because this is f of g of a minus f of g of a. So this equation is true everywhere. It's true everywhere. Except, well, not true for h not equal to 0. H not equal to 0. Okay, so the first part of the proof, we have to show that phi is actually continuous at 0. Because as we said, we wanted to split the limits. We can only do that if the limits exist, so we'll prove phi is continuous. For every continuity proof, we have to start by let epsilon greater than 0 be given, or fix some epsilon greater than 0, in other words. So the first assumption we need to use is that f is differentiable at g of a, which we said in the theorem statement, so we assume that. if f is differentiable, then that means the difference quotient, which I've written here, this difference quotient as a limit exists, and its value is given by the derivative. So if the limit exists, then by definition, we can always find a delta given epsilon. So epsilon is handed to us. We've already fixed epsilon. Given that epsilon, we can find a delta, which I will call delta 1, so that whenever, now I'll use k, because h has already been used, but whenever 0 is less than the absolute value of k is less than the delta 1, which we've picked, then the difference between the difference quotient defining f prime of g of a and its value, f prime of g of a, is less than epsilon. So this whole thing is just the big, g of x minus g of a, right? Or L if you prefer, in our limit proofs. This is just the second part of the statement, that the function is epsilon close to the limiting value. It just looks more complicated because the function here is the difference quotient defining the derivative. Okay, so I'll call that 1, because we're going to refer to these equations in the following slides. So I'll call this equation 1 in what follows. The second is that we've assumed g is differentiable at a, and as we've seen, whenever a function is differentiable, it's automatically continuous. So we will use that assumption. G is continuous at a, which means its limit exists at a and is equal to the function's value. So now, you have to be careful here, because we're kind of concatenating our epsilon delta definitions. We picked a delta 1 in the first step. Now we're going to use that delta 1 as the epsilon in the second step, right? This is the thing that the function output has to be within a tolerance of. So this is kind of the quote-unquote epsilon, you would say. We use that delta 1 as the epsilon in the continuity argument of g, and choose a delta 2, so that whenever h, we don't need the 0 because of continuity here, whenever absolute value of h is less than delta 2, then g is delta 1 close to g of a. So those are our two steps. The two steps we'll use in the next two slides. Use differentiability to get condition 1, use continuity of g to get condition 2. We'll need both of them. And remember, our goal is to show phi is continuous at 0 as a first step, which we'll do on the next slide. Okay, questions on this stuff?
I do not have any questions.
Okay. Good, we will carry on then. Alright, so now, as I say, we want to prove that phi is continuous at 0. So its limit as h goes to 0 is its function value at 0. Here's the proof of that part. So recall that we already fixed an epsilon, so epsilon is handed to us. Now I have to prove that if the input h is less than delta 2, so this is the choice from the previous slide in condition 2. If h is less than delta 2 in absolute value, we need to prove that the output is epsilon close to f prime of g of a. Now here's where you have to be careful, because there's two cases. We could have g of a plus h minus g of a equals 0. This could hold for some values of h, even if h is not equal to 0. So for instance, if g is a constant function, then we would have to worry about this even when h is not equal to 0. So we have to handle this case explicitly. But the nice thing is that in that case, it's very easy to prove that phi of h is close to f prime of g of a, because if g of a plus h minus g of a is 0, let's go back and look at the definition of phi. If g of a plus h minus g of a equals 0, then phi is exactly equal to f prime of g of a, by definition. So in this case, when g of a plus h equals g of a, phi of h equals f prime of g of a, so this is 0, which is always less than epsilon. So that case is easy. The second case is when g of a plus h minus g of a is not 0. So in that case, suppose it's not 0. We define that difference to be the variable k. And then, by definition, again, when this thing is not 0, we look at the definition of phi in the top part of the piecewise and use the definition of k, right? So k was g of a plus h minus g of a. So in terms of k, g of a plus h is k plus g of a. Because if I add g of a to g of a plus h minus g of a, I get g of a plus h. It's the adding zero trick. So in terms of k, phi of h is f of g of a plus k minus f of g of a over k. So now this is where we use condition 2. So condition 2 is this thing. We've assumed h is less than delta 2 in absolute value. We've defined this thing as k. So condition 2 tells us the absolute value of k is less than delta 1. But that's great, because then if that's true, we can use condition 1, because if the absolute value of k is less than delta 1, then this whole thing is less than epsilon in absolute value. But as we'll see in a moment, just by looking back at the previous slide, that thing is exactly phi of h minus f prime of g of a, right? Because by the definition we've just made, this thing is phi of h. So there's a chain of implications, right? We assumed this, that implies this, and that implies this thing in 1, which implies this thing, which is what we wanted to prove for continuity. So we use first 2, then 1 to conclude that the absolute value of phi of h minus f prime of g of a is less than epsilon. So that completes the epsilon delta proof of continuity of phi, which was the first thing we need to prove the chain rule. So now we've proven phi is continuous at 0. That was the hard part, continuity of phi. Yeah, I imagine perhaps not all of the details made sense, but if you are not totally lost in the weeds at this point, you should ask it like a big picture question or a clarifying question.
I like how you silently knew that you had to add the semicolon.
How could I forget? Okay, if you don't have a question, I will ask you a question. Can you summarize in like 1 to 2 sentences the big picture of the flow of the proof, the strategy that we're doing?
I don't think I can summarize it.
Okay, can you, even if you can't summarize, can you, if someone asked you right now, if like Mason or your mom or someone walked up to you and said, tell me one sentence about what you just done in the past 10 minutes, even if the sentence is, we're trying to prove the chain rule and I'm confused, what would you summarize the last, 5 minutes of discussion as?
Trying to pay attention, but it doesn't work.
Ah, okay. Is there something, do you have distractions around you or something?
No, it's just that I'm paying attention and yet I don't understand.
Okay. All right, I'll try to just back up and make 1 or 2 big picture comments. So the big strategy is we're trying to prove the chain rule. The chain rule is this statement. We made a trick, which is splitting the limit whose value we're trying to evaluate into 2 functions. One of them we're calling phi. Then we're trying to massage the stuff inside the limit so that we can split this into 2 separate limits. But we've seen that you can only split a limit of a product into 2 separate limits if both limits exist. So we have to prove that the limit as h goes to 0 of phi exists. And to do this, since we have chosen a value for phi at h equals 0, it suffices to prove that phi is continuous, which means that its limit as h goes to 0 is equal to this thing. So we tried to do this, that's what we did in this slide, the next slide. We were trying to prove that the limit as h goes to 0 of this helper function phi that we're defining to prove the chain rule, the limit as h goes to 0 of phi is this thing. That's what we're trying to prove. And that required a fairly detailed technical argument, so we had to do some epsilon management. We fixed an epsilon, we used the assumptions of the theorem, differentiability of f, continuity of g. We did this complicated chain of choosing multiple deltas to guarantee the epsilon definition is satisfied. And at the end of the day, at the end of this slide, we got the thing we wanted to show to split the limits, that phi is continuous at 0. So that's fine. If the last two slides don't make sense, just get that big picture. Phi is this helper function for the chain rule. We've proved it's continuous. Okay. So now we can conclude. So with all that preparation, now the proof is very simple. It's just a few lines of calculation. So what is the proof? We need to prove this limit exists because it defines the derivative. So as we've seen by algebra, this limit, whenever h is not equal to 0, is the same as phi times this thing, the difference quotient for g. We defined phi, by the way, so that this would be true. So this is true by algebra. Now, this step is because both limits exist. Why do both limits exist? Well, we proved that phi is continuous at 0 in the last two slides, so that limit exists. This is because g is differentiable. We've assumed g is differentiable in the theorem statement, so this limit exists. And if both limits exist, we can split the product. But then we're done, because if phi is continuous, this factor gives us the first thing, and if g is differentiable, this is the definition of the derivative of g. So we simply evaluate those two. And that's the proof of the chain rule, because now we've proven derivative of f of g of the derivative of f of g of x at a is f prime of g of a times g prime of a. Okay, hard proof, but it uses everything we've learned basically in this group so far. It uses the epsilonics, maybe not everything from chapter 1, but everything in chapter 2 and chapter 3 so far was used in this proof. I think it's a very nice proof, even though it's hard to follow. Okay, thoughts or questions on this stuff?
I do not have any thoughts or questions.
Okay, good. This is an exercise in practicing, trying to extract the big picture, even if you're getting lost in the weeds, which is useful. But okay, well, let's back up from the abstraction and try to apply this to an explicit example again. So, I mean, even if you don't understand the proof entirely, we'll accept the chain rule as true. So now we'll use the chain rule to get a second proof of the derivative of cosine of x. So pretend we don't know what the derivative of cosine is, even though we proved it last time. We want to derive it again. But suppose you do know the derivative of sine is cosine. So here's my challenge to you. Begin with Pythagoras that for any x, sine squared of x plus cosine squared of x equals 1. Now take the derivative of both sides. So you'll tell me what the derivative of both sides are. It'll give me an equation, and somewhere in that equation will be the derivative of cosine. So if you like to make it easier to read, we can define a new function, say f of x, which will be the derivative of cosine. Oops. Cosine prime of x. And then we're going to solve that equation for f of x to determine what the derivative of cosine must be. Okay, so my challenge to you, if I take the derivative with respect to x of both sides of this equation, what new equation do I get?
Are you asking without manipulating it algebraically?
Yeah, just like straight up read me the derivative of this term, the derivative of this term, the derivative of this.
Are we applying the power rule?
Power rule and chain rule.
Oh boy.
Well, we can start with sine squared of x, right? So this is sine of x, whole thing squared, right?
So I believe that that is going to be cosine x squared.
No. So
No.
what's the derivative of the outside function? So the outside function is something squared, right? So what's the derivative of, say, x squared?
Okay, I see. That's going to be 2 cosine x.
No. So this should be 2 times the inside
What's
function
I
left
missed?
alone times the derivative of the inside function, right?
Okay.
Good. So 2 times sine x times cosine x. Okay. So is it clear why this is the right procedure, by the way? So this is like x squared goes to 2x, where here x is sine of x, so the derivative of the outside piece is 2 times sine x, and then you multiply by the derivative of the inside, which gives you cosine times x prime, say. So are we happy with why this should be 2 sine x cosine of x? Or should I write this out more carefully?
Proven both the power rule and the product rule, not product, what we are currently looking at, but I don't understand why. Okay.
Should I write out the composite more explicitly? Would that help?
I don't understand why we need to make a composite if we proved previously that n to the power x, no, x to the power n equals nx to the power of n minus 1.
Yeah, so we proved that's true for the variable x. So we proved
So just straight up x.
only x. All that we proved is d dx x to the n is nx to the n minus 1. It is not a consequence of that d dx of some other function f to the n is nf to the n minus 1. This is not true. Only if it's x inside, right?
See, the problem is I was thinking substitute anything in for x.
You can substitute anything in for x, but that doesn't change the derivative on the outside. So you could substitute whatever you like for, say, now I've run out of erasing. So it's not true that d dx of, say, f to the n, this is not the same as the derivative with respect to f of f to the n, right? So you can substitute whatever you like for x, but that doesn't change the derivative acting on that thing on the outside, right? It just changes the thing on the inside. This thing, ddf of f to the n, is nf to the n minus 1. But that's not the same as ddx of f to the n. This is nf to the n minus 1 times df dx, right? So the letter appearing in the derivative you're taking with respect to certainly matters. This is very similar to the dummy variable argument in g of x plus t. If this is f of t versus if this is f of x is g of t plus x, right? The expression that this thing depends on is quite important, right? Important point though. More questions on this thing.
So what you just wrote down that I don't totally understand, that is what is preventing us from saying that replacing in the product rule that x equals sine of x? Substituting, I mean.
Yeah, since let me write it out for that case, maybe for the sine of x. So okay. So let's say we've proven, so true. We have proven d dx of x squared equals 2x. So you can replace x as a dummy variable in this equation. So I agree, which is what you're suggesting, that we can replace x everywhere with sine x. So dd sine x of sine squared x is 2 sine x, right? Because we've just replaced the dummy variable everywhere. The false thing is ddx of sine squared x equals 2 sine x. You shouldn't expect this equation to be true because you started with a true equation and replaced 2 of the dummy variables, but then didn't replace the third one, right? You can't replace some dummy variables with sine x and then leave some of them unreplaced and expect the equation to still be true. So this is not the case.
So now I am confused by the form ddx.
So this Leibniz notation of ddx. Good. Okay, so what does this mean? So the expression ddx is meant to say that if you have a function f of x, let's compare this with the Newton notation. So f of x is a function of x, then f prime of x in the Newton notation is, of course, the limit as h goes to 0 of f of x plus h minus f of x over h. And then Leibniz says, here is my notation. Use ddx of f to be, I put 3 bars for a definition. We define this to be the same as f prime of x. So now you ask, okay, what is the meaning of the letter x in ddx? So the meaning of the letter x is to say, look at the function which this thing acts upon, and if that function depends on the same letter appearing in my ddx, so if f is a function of x, then this expression is equal to the difference quotient which would define the derivative f prime of x. So as an example of where this would be different, if this were, say, f of y, and y does not depend on x, then ddx of f of y would be 0. Because this would say, okay, this is take a difference quotient of something which doesn't depend on x at all. Well, that's going to be 0 minus 0 in the numerator, and the limit identically vanishes. But if this is something inside, say, f of sine x, something different which does depend on x, then the Leibniz notation, by definition, means to use the chain rule. So you could take this as a different definition if you like, since the Leibniz notation with this ddx is, I guess, kind of sloppy. But this is the precise definition we mean of ddx of some composite function. This means what you would get by the chain rule. So this means f prime of sine x times the derivative of the inside, which is cosine of x. Good. So you have to be careful about which of these variables you're differentiating with respect to. Better or worse? Did that help?
Still not understanding the with respect to.
Yeah, so that's just a common terminology. One says you're differentiating with respect to x when x is the variable that, or the letter which appears in the denominator of Leibniz notation, or in other words, if you, in Newton notation, are taking a limit as h goes to 0 of some function of a variable plus h, then you say, we use the words, this limit is the derivative of f with respect to x, because x is the argument that we are shifting by h and comparing the difference between. So if your difference quotient is, shifting the argument x, then we say that this is taken with respect to, WRT, with respect to x. Same thing here, with respect to x. More thoughts?
So now it looks like that the Leibniz notation just made it more complicated for no reason.
Oh, this one?
Correct.
Yeah, Spivak has that opinion. So in Spivak he prefers Newton notation and calls Leibniz. He throws some shade on the Leibniz notation, this DDX, and says that this is like an abomination. And then he has some exercises where he writes things like this and says, examine these specimens of Leibniz notation and see if you can figure out what they mean. Where by what they mean he means expressing them this way. So yeah, that's fine. You are entirely within your rights to say that this operation of DDX. It's more complicated because you have to remember, okay, I have to kind of consider the chain rule if this is something that depends on X and so forth. So I agree that this is a more loaded notation. Yeah, sadly, this is also the more common notation, I think, in science. I mean, this is more common in mathematics. This Leibniz notation, I think, is more common in science because you're often taking derivatives of functions with several variables, so it's good to have an explicit reminder of which variable you're differentiating with respect to. So yeah, that's fine. Yeah, I agree this one is more clear for pure math.
I still don't believe I'm totally understanding, but at this point I don't think that there's anything further that can be done.
Okay, well, we will keep chugging ahead and perhaps it will become clearer from doing more examples. So let's test this understanding of chain ruling. See if you can write down or tell me what to write for the derivative of cosine squared of x, where remember, we're pretending we don't know what the derivative of cosine is, so we're just going to call the derivative of cosine f. So doing that, what's the derivative of cosine squared?
Is this going to be... Oh, let me think. 2 cosine x times cosine prime of x?
Yeah, which we're calling f, so good. So 2 cosine of x times f of x. Good. Now derivative of the right side of the equation.
I believe that 1 is a constant and therefore its derivative is 0.
Good. Okay. So by differentiating Pythagoras, we've gotten this equation: 2 sine x cosine x plus 2 cosine x f of x equals 0. And pretty obviously we can cancel 2's, factor out a cosine of x, so I'll just do the factoring. Cosine x times the quantity sine x plus f of x equals 0. So now, by the zero product rule, either cosine of x is 0 for all x, which is not true. We know that cosine of x is only 0 for certain values of x, like pi over 2 or 3 pi over 2. It's not always 0. So since that's not always 0, it must be that the second factor in this product is always 0. So from this we infer that f of x, which is the derivative of cosine of x, must be minus sine of x, because we set their sum to 0. So again, this is cosine prime of x is minus sine of x. So by differentiating and using the chain rule, we have now supplied a second independent proof that the derivative of cosine is minus sine. Good. Thoughts on this?
I do not have any thoughts or questions.
Sweet. Okay. More stuff. Yeah, this is the same thing. Chain rule: 2 sine x cos x, 2 cos f. Either this vanishes or f is minus sine, which indeed it is. Good. Oh yes, I have one more challenge for you before doing inverse functions. So before we prove this 1 over f rule, that if f is differentiable at a and f is non-zero, then the derivative of 1 over f is this thing, minus f prime over f squared. So I'll ask you, how would I prove this using the chain rule? So in other words, well, I know this is going to trigger you, but I'll write ddx. What is ddx of 1 over f of x, which, to be somewhat more explicit, we can write as a composite function, f of x raised to the power minus 1. So what should I do using the chain rule to differentiate this expression?
So is it correct to apply the product rule here? No. I mean, for our first part, is it? I think.
You mean power rule?
Thinking. Yeah, power rule.
Yes.
We're
So
messed up.
we can use the power rule because we proved the power rule for integers, and -1 is an integer, so we're in good shape there.
Wait, I thought we proved it only for natural numbers.
Remember we proved it for natural numbers, then we proved the 1 over f rule, so we proved this before, and then we used the 1 over f rule to prove that it's also true for negative numbers, negative integers. So yeah, I guess if we hadn't already proved this in a separate way, this proof would be kind of circular, because we used this proof to prove the power rule for negative integers, but we're just providing a second proof, so this is still logically valid. But yeah, to answer your question, we did prove it for negative integers as well.
Okay, so we have that. This is going to be equal to, let me think, negative f of x to the power of -2
Good.
times English, f prime of x.
Good. And this
Not even English, it's math.
it's some distorted version of English. Yes, okay. And then using our negative power rules, we can just pop that bad boy in the denominator with a square. So, indeed, so that's exactly what we proved using kind of a more laborious limit calculation. Remember, we had to do some epsilon deltas to prove this thing. Here we can prove it directly from the chain rule, although you might argue, well, you had to do even more epsilon delta arguments to prove the chain rule, so that's probably even more work. But good. All right, questions on this?
I have no questions.
All right, time for some more hard proofs then. Your break of solving problems is ended. All right, so now we want to differentiate inverse functions. By here I don't mean, we already know how to differentiate a multiplicative inverse like 1 over f. Now I really mean the honest-to-God inverse function, like f inverse of x. So this will be very important, but also rather challenging. So first let's review how inverse functions work. So our working definition of functions are just collections of pairs of numbers, so any collection of pairs of, say, real numbers, with the property that if two pairs, a, b, and a, c, are both in the collection, then b must be c. So you cannot have the same x value and different y values in your table of values for the function. That's just another way of saying the vertical line test, right? So you can't, to be a function, you cannot output, say, you can't have something like this where you're going to map 1 to 5, map 2 to 3, and then map 1 to 7. You can't do that, because then that's not a function. It has to be at most one output for each input. So that was our definition of function. To have an invertible function, or an inverse, as we saw in Chapter 1, you need an additional condition, which, I don't know if we use this word, but this condition of passing the horizontal line test is sometimes called being 1-to-1, or especially in topology and linear algebra, you call this injective. So what does 1-to-1 or injective mean? It just means that whenever your inputs are not the same, your outputs are not the same. You cannot feed into the function two different inputs and get the same output if you want to be 1-to-1. So I like the words 1-to-1 because just saying 1-to-1 kind of suggests what the definition is, right? So here is an example of a function which is 1-to-1, right? This function simply maps 1 to d, 2 to b, 3 to c, 4 to a. And here is an example of a function which is not 1-to-1, because this function maps 1 to d, 2 to b, 3 to c, and 4 to c. So we have two different values, a and b, but f of a equals f of b, even though a is not equal to b. So this is not 1-to-1. So as we saw, you can only have an inverse function if your function is 1-to-1. Just review. Questions on this?
I have no questions.
Sweet. Onward. Alright, so a challenge for you. This is exploration. This is not a proof. I have to emphasize this doesn't prove anything. We're just going to explore and guess what the answer for the derivative of an inverse function should be and then once we guess it, we're going to prove that it's right. So this is very sketchy, because we're just going to assume that f and f inverse are both differentiable. We have no reason to assume this at all, so this is just boldly ignoring the question of whether the derivative exists. It's wishful thinking. But to explore, let's just assume that's true. Now we're going to use the chain rule. By the definition of an inverse function, we saw this in chapter 1 many times, that the definition is that for all x's that are in the domain of f inverse, which we're ignoring the question of whether it's in the domain for now, because we're just exploring, we have this equation f of f inverse of x equals x. So now I will ask you in this challenge, just to trigger you, I'll put a ddx with square brackets around everything. If I take the derivative of the left-hand side and the right-hand side of this equation, what do I get? First the left side, what do I get?
Here we go.
By the way, just to emphasize, this does not mean raised to the minus 1 power. So you do not use the power rule. F inverse is just a function.
I believe it to be f prime of inverse f of x equals 1.
Alright, I'm going to put a space here because we forgot something.
Ah, right.
What
Lovely.
What goes in the derivative of the inside piece?
Inverse of f of x prime.
Good, so f inverse prime of x. So this takes some LaTeX wizardry to typeset something like this, because you need iterated superscripts. But okay, now easy step. Remember, we're trying to get a formula for the derivative of the inverse. So just solve this equation. If you solve this equation for the derivative of the inverse, what do you get?
We can divide both sides by f prime of inverse f of x.
Good. So f inverse prime of x equals, as you say, 1 over dividing f prime of f inverse of x. So, I mean, I'm gonna put box around that because we haven't actually proved anything. We just guessed the answer. In fact, this is the correct formula for the inverse function's derivative in terms of the derivative of the original function. So we've guessed the answer, but we have to prove that if f is differentiable, then f inverse is differentiable, because otherwise, I mean, we've only proven the chain rule assuming that both of the functions being composed are differentiable. So if we don't prove that f inverse is differentiable, then the first step of our argument is invalid because we've applied the chain rule to a function without knowing it's differentiable. So we have to back up a little bit and actually justify this answer, which will require some proofs. We have, I think, 3 proofs we have to go through to build up to that. But before we dive into the 3 proofs, questions on this exploration step?
The inverse.
Oh, sorry, you cut out. What'd you say?
Moving slightly closer to the mic. So the derivative of the inverse is the inverse of the derivative.
Yeah, but you're using the word inverse in 2 different ways in that sentence.
Oh boy, I didn't even realize that.
The derivative of the inverse function is the multiplicative inverse, 1 over the derivative of the original function evaluated at the point, which is the f inverse of x. So there's a lot going on in this formula, right? The derivative of the inverse is 1 over f prime at f inverse of x. So to compute this, you need to know what x is, and then you have to find what is the number f inverse of x, then you have to plug that number into f prime. So it's quite complicated, but yeah. Good question. Other questions?
I have no question.
All right, let's first an intermediate result that we will need to prove that formula. Oh, well, here's what we just did. It's 1 over f prime of f inverse of x. Same thing. All right, so first we're going to need to prove that f inverse is continuous, then we're going to prove that it's differentiable, but to prove that f inverse is continuous, we need a lemma. And this is actually related to a comment, a very prescient comment you made in the tutorial with the converse of the IVT. I don't know if you remember this, but when you were proving the converse of IBT, and at the end of the tutorial I asked you, can you just explain the big picture of what it is that we just proved? And you said that, well, IBT tells us that if you're continuous, you hit all the points in between. And we didn't quite prove that if you hit all the points in between, then you're continuous. But we proved that if you hit all the points in between and you take on each value once, then you're continuous. But you answered it in a very an interesting way, because when I pressed you and said, what did we actually prove? You said, we proved that if you hit every value in between, and you're either strictly increasing or strictly decreasing. So you said this instead of taking on, taking on each value only once, you said strictly decreasing or strictly increasing. Which I thought was a very interesting comment, because that's true. It is true that if a continuous function takes on each value only once, it must be either strictly decreasing or strictly increasing, even though we haven't proven that. But now we actually do need to prove that. So the thing that you guessed when you answered that question was actually true, and now we'll prove it. So here's the lemma. Suppose f is continuous and one-to-one, which we've just defined. It means it passes the horizontal line test, on an interval. Then f is either strictly increasing or strictly decreasing. So first a comment. This is obviously not true if the function is discontinuous, right? So the function can be one-to-one and not be strictly increasing or strictly decreasing if it's allowed to jump, right? So you could have a function like this. It does, I don't know, something like that. So if the function is discontinuous, I should have made that an open circle. If the function is discontinuous, this is clearly one-to-one. It passes the horizontal line test, but it's not always strictly increasing or strictly decreasing. It's increasing here, it's decreasing here, then it's increasing again. So this theorem fails if f is discontinuous. And we know if the lemma fails when f is discontinuous, we're going to have to use continuity somewhere in the proof. Okay, so how does the proof go? There will be 3 steps again. They're all pretty simple. It's just kind of ordering points. So the first thing we'll prove, remember this thing's defined in an interval. So we'll take 3 points in the interval, and we'll prove that either the function values at those 3 points are increasing in a chain, f of a is less than f of b is less than f of c, or they're decreasing in a chain, f of a is greater than f of b is greater than f of c. Then we'll extend that to a chain of 4, a, b, c, and d, and then we'll finish the proof. So to finish the proof, the reason we need 4 is because we know the function's defined on an interval, and by the definition of strictly increasing and strictly decreasing, we have to consider any 2 points that are not endpoints in the interval. So because the definition requires the endpoints of the interval and any 2 points inside, we actually need to prove this chain for 4 points, which is why I'm building it up in steps. Okay, let's do the first one. So I'll prove the first thing. Let a, b, and c be 3 points in the interval, and I'll handle the case where f of a is less than f of c. So a similar argument applies. Just switch all the inequalities. If f of a is greater than f of c, the whole argument goes through the same way. You just flip all the inequalities the other way. So proof by contradiction. I'm trying to prove, want to prove, that f of a is less than f of b is less than f of c. So I'm going to suppose by way of contradiction that this is not true. This chain of 3 inequalities, or 2 inequalities with 3 terms, will be not true if either f of b is less than f of a, or f of b is greater than f of c. So I have to prove you get a contradiction in either of those 2 cases. So why do I get a contradiction in those 2 cases? Well, my hand-drawn diagram here is a little bad, but let's consider the first case. The first case is that here's A, here's B, and here's C. If you assume by way of contradiction that f of B is actually smaller than f of A, then all you do is apply the intermediate value theorem. So you say, aha, I can apply the intermediate value theorem on this interval because f is assumed continuous. And in particular, I apply the intermediate value theorem to the interval BC. And I use that to find some point in that interval such that f applied to that point gives me f of a. Right? I can do that because f of b is less than f of a is less than f of c in this assumption. But that contradicts the assumption that f is 1 to 1. Right? So f is 1 to 1. And now I've just found two places where it takes the same value. So that's a contradiction. Or Bank of Scotland. Same thing the other way. Very similar argument. If instead we assume by way of contradiction that f of b is bigger than f of c, so f of b is up here, you do the same thing. You apply the intermediate value theorem to find a point in the interval ab, which is the same as f of c. And now f fails the horizontal line test again. So again, contradiction in this case. So this proves for 3 points that they have to be either ascending or descending in a chain if f is continuous and 1 to 1. Okay, questions on this? Either you have push to talk on or you're in deep thought.
On?
Are you saying things? I don't hear things.
Test.
Ah, now I hear test. Okay.
Lovely. I had to remute myself.
All.
I mean like mute and then unmute for whatever reason. Why is think there twice?
I don't know, because so there was just like many seconds of silence, and I was trying to fill the awkwardness by writing things, but perhaps you were talking and I couldn't hear you.
Yeah, I was talking and you couldn't hear me.
Okay, what were you saying?
I don't have any questions.
Ah, okay. Alright, so that was the 3-point case. Let's prove the 4-point case. It's pretty easy. If there's 4 points, you just apply the 3-point case separately to the first 3 and the second 3, right? So if there's 4 points in the interval, apply part 1 to ABC. That means either they're ascending or descending. F of a is less than f of b is less than f of c, or f of a is greater than f of b is greater than f of c. Apply it again to B, C, and D. Same thing. Either they're ascending or descending. But if both of these are true, then it must be that either it's strictly ascending in all 4 or strictly descending in all 4. I could not have that the first 3 are ascending and the second set of 3 are descending. I can't have both of these because the first one implies f of b is less than f of c and the second one implies f of b is greater than f of c. So I can't have this combination. The only combinations I could have are both ascending or both descending. So that's the pink. Both ascending is the blue. So pretty intuitive, I think, that if 3 have to be ascending, then a set of 4 have to be ascending, and if the 3 are descending, then the 4 are descending. And then this effectively proves the claim. Now we're basically done. We're trying to prove that f is either strictly increasing or strictly decreasing if it's continuous and 1 to 1 on an interval a to d. Now we have enough to prove this. All you do is look at the 2 endpoints. The 2 endpoints, if f of a is less than f of d, then if you hand me any 2 points in the interval, by 2 I can form the 4 points a, b, c, d, and then it must be ascending. Similarly, if f of a is greater than f of d, and you hand me any other 2 points in the interval, then by the results of part 2, the whole chain must be descending. So it's strictly decreasing. So that's the proof. If f is continuous and 1 to 1 on an interval, it's either looking like this, or it's looking like this. Those are the only possibilities, which I think you intuited before when you said it in the tutorial, but you still have to prove it. So, good. Questions on this proof?
I have no questions. I had to get a screenshot of your graph quick.
Why? What's wrong with this graph?
Slack later.
Okay. I probably did something funny, but I don't know what it is. Okay.
I'm ready to go on.
Wait, what'd you say?
I'm ready.
Okay. Alright, we have two more things to prove. So we never proved this, that if a function is continuous on an interval and it's one-to-one, so its inverse exists, then the inverse function is also continuous. I mean, this is very important. We need this to prove, for instance, that the logarithm is continuous, because we define the logarithm as the inverse of the exponential. So we better prove this. Thankfully, a moment ago, we have this lemma that if a function is continuous and one-to-one on an interval, it's either strictly increasing or strictly decreasing. That will be useful. So I will assume without loss of generality that of those two options, it's strictly increasing. If it's not strictly increasing and is in fact strictly decreasing, then you can just replace f with minus f everywhere in this proof, and then minus f will be strictly increasing, and you could get the same argument. You would prove that minus f inverse is continuous, but that implies that f inverse is continuous. So we can just assume it's strictly increasing. Now this is where we have to get into the weeds with some epsilon deltas. So to prove that f inverse is continuous, continuous means the limit exists at every point and it's equal to the function's value. So we have to prove the limit as x goes to b of f inverse of x for any b happens to be the same as f inverse of b. And since every b in the domain of f inverse is in the range of f, we can say that any such b equals f of a for some a in the domain of f. So that's our setup. Now we're going to prove that the limit exists. So to prove a limit exists, as always, we say let epsilon greater than 0 be given. Now I'm going to write out the definition because it looks a little fucky because of the inverse functions. So notice that we're trying to show that if you choose delta such that the input to the inverse function is delta close to b, which is f of a, then the output, which is f inverse of x, will be epsilon close to f inverse of b, which is a. So, I mean, it's hard to follow, but the first statement is that the input to f inverse, which is x, is delta close to f of a, which is b. So by the way, this is b. We need to prove that we can find a delta such that when this is true, then f inverse applied to x will be epsilon close to f inverse applied to the function point, the limit point in question, which is f inverse of b, which is a. So it looks backwards, right? Normally the inequality that has f of x involves epsilon, and the one involving x has the deltas. But now they're backwards because it's an inverse function. So just watch out for that. This is what we have to prove. So want to show this. Okay, how do we prove that? Here's a picture that will give us the idea of how to prove it. So here I'm plotting f of x, but you should really think of this as the inverse function. So the inverse takes a point here, well, a point on the, so it takes this and then maps it. I'll put the arrow for the direction it maps. It takes a point on the vertical axis and maps it to a point here on the horizontal axis. So this is the inverse function. Okay, so we're trying to choose a delta on the horizontal axis such that if we are within that delta of b, then we're going to land within epsilon of a. How do we do that? Well, the idea is to simply look at a plus epsilon and a minus epsilon. That's going to give us some range. After applying f inverse, it will give us some range of values in the input space. Now, we want to make sure that we restrict our inputs to the inverse, which are these things on the horizontal axis, we want to restrict them so that we always land within this range. So one idea for doing that is just take the minimum of whatever these two are, the two distances in these bars, right? So in other words, we're trying to choose a distance on the horizontal axis so that we always land within these bars on the vertical axis. And the kind of obvious way to do that is just say, well, take whichever of those distances is smaller. In this picture, this distance is smaller, so if you want to guarantee that you never fall outside this interval, you should make sure that you are stuck within the smaller distance to one of those two endpoints, a minus epsilon and a plus epsilon. That's the picture. So it's kind of shaded. I don't know if you can tell, but it's shaded on the vertical axis a little bit. That this is the delta we want to pick. So I mean, it's easier in the picture. In math, that's just saying delta is the minimum of f of a plus epsilon minus f of a, which is this thing, and f of a minus f of a minus epsilon. So here's a minus epsilon, so that gets mapped to this point. So we're taking the minimum of this point and this point, or that distance, I guess, which happens to be this one. Okay. This is, I realize it's fairly complicated, but questions or thoughts on this setup or the choice of delta? Because that's the important step in the proof, is how we pick delta.
I didn't have any questions or comments.
Okay. Alright, so let's finish the proof. If we choose that delta, we have to prove that we are epsilon close on the horizontal axis, which is the output of the inverse. So by construction, with this delta, we know that if you apply f to a minus epsilon, which is this endpoint, and if you apply f to a plus epsilon, which is this endpoint, you've chosen your delta to be the smaller of the two. So it's always going to be the case that f of a minus epsilon is less than or equal to f of a minus delta, because we've chosen delta to be the difference between these two things. And in this case, f of a plus epsilon, the top one, is certainly going to be larger than, in this case strictly larger than, f of a plus delta. So we've chosen delta to be the smaller distance. So if you add the smaller distance, you cannot reach up here to the top. This thing must be greater than f of a plus delta. So this implication is the key. On the next slide, we'll take this implication and apply f inverse to it. So let me show you that. Take this implication. This is the implication from the previous slide, so this is from the last slide. Here is where we use the increasing assumption. So if a function is increasing, its inverse is also increasing. And if the function is increasing, then you can apply it to an inequality and it preserves the direction, right? If it weren't increasing, you couldn't apply it to an inequality. It would destroy the inequality. But since it's increasing, we apply f inverse to all three of these terms. You apply it here, apply it here, apply it here. That gives you the next line. And now for the key step, because f is 1 to 1, normally we can't left cancel an inverse like this, right? As we saw with sine and sine inverse. You can't do that because, in general, sine is not 1 to 1, because it has wiggles. In this case, we've assumed f is 1 to 1, so f inverse of f does left cancel. So we cancel the f inverse f here, and cancel the f inverse f here. And that gives us exactly what we wanted to prove, because then what we're left with is a minus epsilon is less than f inverse of x is less than a plus epsilon. I'll just rewrite that in absolute value notation here. That just means f inverse of x minus a, absolute value, is less than epsilon. But this thing that we've just gotten, that's exactly what appears in the definition of the limit. Right? So we've proven that whenever, with our choice of delta, we've shown the reader how to choose a delta, and with that choice of delta, f inverse is always epsilon close to the value it reaches. So that proves the inverse is continuous. So again, tricky proof. Don't need to understand all the details, but the real key picture was just that one from the last slide with the a and the f of a equals b. That thing. That was the key picture, I think, is just realizing that if it's 1 to 1, you can basically trade your deltas for epsilons by pushing along the function. Questions on this?
I do not have any questions.
Okay. One more proof, and then you'll have a reprieve with some exercises, unless you have to leave early. Unless we think we're going long to the discussion of chemistry at the beginning. But alright, so at long last, the thing that we guessed but did not prove, we will now pay the piper and prove this rigorously. So suppose f is continuous and 1 to 1, and suppose f is differentiable at a particular point, f inverse of b. We'll have to assume that the derivative is non-zero, because we're going to divide by it. So we assume f prime of f inverse of b is non-zero. Then here's what we wanted to prove. F inverse is also differentiable at b, which allows us to apply the chain rule, which we did in the guess, and indeed the derivative is given by the formula we guessed without proof. Alright, a little hard proof, but let's do it. So again, if b is in the domain of the inverse, it's in the range of the function, so that means b equals f of a for some a. Good. The limit we have to prove exists is the definition of f inverse prime at b. By definition, that's the limit as h goes to 0 of f inverse of b plus h minus f inverse of b over h. In going from this step to this step, all I've done is replace f inverse of b with a, right? So that follows from this equation. If b equals f of a, then a equals f inverse of b. So we just have to prove this limit exists. Now again, I said this a moment ago, but I'll repeat it. Every number in the domain of the inverse function can be written as f applied to some number in the domain of the function itself. Or sorry, it's in the range of the function, so that means it's f applied to something in the domain of the function. So we're going to define a number k with the property that b plus h, which is in the domain of the inverse, is f applied to a plus k. When you've made that definition of k, we can simply replace b plus h in the definition of the limit up here, replace b plus h by f of a plus k, which is what I've done, how I've defined it up here. And then again, since f is 1 to 1, we can left cancel. This is why we did this. Because if you left cancel f inverse against f, you're left with a plus k minus a, which is just k upstairs. Okay, so everything so far has been just juggling variables. We've defined a k and re-expressed it in terms of this k. So now I will ask you a challenge. Take this equation, b plus h is f of a plus k, use this and solve algebraically, and tell me what is k. Solve for k, and your answer can involve f inverse, b, or h, but it should not involve a. So what do you think? Take a minute to think about that.
So is this going to be f inverse of b plus h minus f inverse of b?
B plus h. Yeah, good. Minus f inverse of b, because you replaced a with f inverse of b. Very good. So that's k. Perfect. Right, and this has a very nice form, because this looks like the numerator of the difference quotient for f inverse, which is good. Okay, so got that. Here I've repeated what you just told me. K is f inverse of b plus h minus f inverse of b, as you say. So here's the key point. F inverse is continuous. That's why we did all that work a moment ago to prove that the inverse function is continuous. So what does continuity mean? Continuity means the limit as h goes to 0 of f inverse of b plus h equals f inverse of b. Right? That's what continuity means. It means if you take the limit as h goes to 0, that's the same as plugging in h equals 0, which would give us f inverse of b minus f inverse of b, which is 0. So that's very useful. So we know the limit as h goes to 0 of this combination, which we have defined as k, that is 0. So limit as h goes to 0 of k as a function of h equals 0. So now we're basically done. Now, I just want to look at one thing we saw in the previous slide. The thing we're trying to compute, which is f inverse prime of b, that's the same as this thing, just by algebra, this thing in the bottom right, limit as h goes to 0 of fac f of a plus k minus f of a. So keep that in your head for a moment, this expression. Now we look over here. This thing is exactly 1 over that, right? So this is 1 over that thing that we were trying to compute a moment ago, which was the derivative of the inverse evaluated at b. Right, the two things, this is fac minus fa over k, and this is k over fac minus fa. So the expression inside the limit are the same, but upside down. Why does that help us? Oh, well, also the variable going to 0. Here it's h goes to 0. Here is k goes to 0. So why does that help us? We've proven that if a limit exists and it's non-zero, then the limit of 1 over that argument, so the multiplicative inverse, also exists. So that was useful. If the limit exists and it's non-zero, then the limit of 1 over that expression exists, and it's 1 over the thing. Okay, so 1 over the thing, this is simply the difference quotient which defines the derivative f prime of a, and a is f inverse of b, which we've assumed f prime of f inverse of b is non-zero. Okay, so then we're done. The last step is simply to say, well, algebraically, f inverse prime of b was the limit as h goes to 0 of this thing. Now there's two steps we need to justify this final equal sign. The first is that the limit as h goes to 0 of k equals 0. So now we can compose these two functions, right? Notice that the variable going to 0 and the limits are different, right? That's a problem. In one limit, k is going to 0, and the other is h going to 0. But you proved, back in consolidation document 2, I think, that the limit of a composite function is the same as you would get by taking the limit of the outer function as the inner function goes to its value, assuming that the outer function is continuous. And here we've proven that. This limit as k goes to 0, limit as h goes to 0 of k equals 0. So we need this to replace the k goes to 0 with h goes to 0 in the limits. So that's one step. One step is, I don't know what to call that, limit of a composite, which we proved. That's the one step. And the second step is the limit of a multiplicative inverse. Multiplicative inverse. Because this thing in the pink box is 1 over this thing in the second pink box. So applying those two theorems that we proved, limit of composite and limit of multiplicative inverse, this thing has to be 1 over the value of this limit up here. So it's 1 over f prime of f inverse of b. So that's what we wanted to prove. Again, pretty hard proof, lots of steps. It has used everything we've learned. But big picture I think you should follow is that what were the ingredients? We needed continuity, we needed one-to-one, we had to assume f is differentiable. The steps in between were a bit complicated, but they used the previous lemmas, in particular the continuity of the inverse, and at the end of the day we proved the formula which we guessed in the exploration. Okay. Questions or thoughts on this proof?
I do not have any questions or thoughts.
Okay. I apologize for abusing you with so many difficult proofs today, but okay. Feel free to tell me to quit and fuck off if you need to leave, because we're coming up on 2 hours since I think we started at 10 minutes after the hour. But if you still have time, we can do some challenges to apply that formula we just derived. So I will repeat the formula. F inverse prime at x is 1 over f prime at f inverse of x. Okay, so that's the formula we derived. Now I'll ask you as a challenge, we're going to find the derivative of arc sine, the inverse sine function, using this formula. So if f of x is the arc sine function, f sine inverse of x, what is the derivative f prime at a? So using this formula, what should I do to get the derivative of sine inverse?
Deep thinking.
Think.
So let me think. Okay, I was just hoping that you would keep writing think.
I have to connect all of them. Okay. Have you had enough time to think while I drew that circle of thinks?
Yes, I did.
Good. What do we got?
What have I gotten? Oh god.
Yeah. What do you think sine inverse prime of x should be?
So this is, you know that sine inverse equals 1 over x, so, I mean 1 over sine x. Let me think more. Okay, we're 1 over, I want it, the idea that is like recursive for whatever reason.
Recursive. Wait, why is it recursive?
Because I keep thinking 1 over sine inverse from, like, I don't know.
Oh, so you're saying, okay, so the formula was f inverse prime at x is 1 over f prime of f inverse. So you're saying this is recursive because the formula involves sine inverse? Because it's down here?
I was saying the outer function.
The outer function, f prime.
Yeah.
Ah, but f prime is the derivative of sine, right? Because this is the inverse. So f prime should be the derivative of the sine function, right? I guess I shouldn't use f in this formula because I've used f in the problem.
Wait, is it? Thinking. So the multiplicative inverse of sine is the, I forget the proper word for, like, functional inverse.
Oh, the inverse function, right? So this is not the multiplicative inverse of sine, right? So sine inverse of x is not 1 over sine x. We have a name for 1 over sine x. That thing is called cosecant of x, right? So these are different.
Okay.
So this is what we call arc sine, right?
Right.
Okay.
And one would have been in a different spot if it was the multiplicative thinking still.
Good. Maybe it's more helpful if I write it this way. So we could define g of x as sine x, and then f of x, the thing that we're looking at, is g inverse. So how do we differentiate, or, you know, we could also write this as f inverse of x equals g of x, whatever, however you like. Now our formula becomes f inverse prime at x is 1 over, well, f, but that should be the inverse of, now I've confused myself. We want, this is f of x is the sine inverse function, right? Good. So this should be 1 over g prime, because g is the inverse of f inverse. g prime of shit. This is not what I want. I don't want f inverse prime. That's why. That's what I'm doing wrong. We're just trying to find, with this notation, f prime of x. There we go. G inverse of f of x. I tried to make it simpler and then I made it more confusing. Okay, so I've just translated the function so that there's fewer inverses around, right? I defined a new function g, which is f inverse. Does that help?
So now I'm trying to remember, I believe that our final answer is going to be 1 over cosine x of sine inverse x.
Good. 1 over cosine of sine inverse of x. Very good. Yeah, because g prime, the derivative of sine is cosine, and then you leave the original function alone inside. So the original function was sine inverse. Good. Now we are helpfully asked by the problem writer, who is me, to simplify until there are no trigonometric functions remaining. So I don't know if you remember this, but we actually did this as a blitz question in chapter 1. I forget which session, I don't know, 10 or 9, I don't know, something. Do you remember how to simplify this so that there are no trig functions left?
I remember it being asked before.
Good, okay. Well, the hint is Pythagoras. Can you see a way to use Pythagoras to simplify this? Cosine of y by Pythagoras is square root of 1 minus sine squared y for any y.
So this is going to be the square root of 1 minus sine squared of sine inverse of x?
Yeah, we should be careful. This is 1 minus, so it's supposed to be sine squared of y. Here y is sine inverse of x, so as you say, it is indeed sine squared of sine inverse of x. But what's that? Well, this is sine of sine inverse of x quantity squared, right? Sine of sine inverse of x is x. So quantity squared should be 1 over root 1 minus x squared, right?
I don't understand that.
So sine squared of sine inverse of x. What does sine squared mean? Sine squared means take the sine of the thing and then square it. So this is sine of sine inverse of x, quantity squared. You can always left act with sine to cancel sine inverse. So sine of sine inverse of x is x. So this is just x quantity squared. Good.
That makes more sense.
Okay. So I find this quite surprising, that you would think an inverse trigonometric function is somehow more complicated than a trig function, so its derivative should be something that involves lots of trig functions. But rather remarkably, the derivative of an inverse trig function, sine inverse, involves no trigonometric functions whatsoever. You can write it as 1 over root 1 minus x squared. So this is, this is why often when doing integrals, if you look at old MIT integration bee questions, which we'll do when we get to chapter 6 or so, 5 or 6 maybe, often there's a trick to do an integral that just involves square roots, where you do some chicanery, some trickery, to replace functions by sine inverses, because sine inverses are somehow secretly related to square roots of 1 minus x squared like this. So it's pretty tricky. But anyway, so that's the derivative. Questions on this?
I do not have any questions.
Good. All right, let's hammer some more until you tell me to staffu. Right, so here's the solution. Yeah, g prime of f of a, as you say, cosine of sine inverse of a, use this thing, use Pythagoras, sine of sine inverse of a quantity squared, 1 minus a squared, and that means the derivative of sine inverse of x is 1 over root 1 minus x squared. Good, same thing I said. All right, another one. So now we know, maybe I'll be a little more explicit again. So if f of x is e to the x, then we know that f inverse of x is log x. So let's find the derivative of the logarithm. What is, I won't use ddx because you don't like it, but f inverse prime of x, which is the derivative of the log function. So what should I do?
So this is slowly forcing me to memorize the rule.
Oh, you will memorize all of them. You cannot pass a calculus course until you have memorized all of these rules.
Lovely. So we are going to have 1 minus, let me think.
Or 1 over, right?
Yeah. I don't know why I said minus. That was just...
Good.
1 minus log prime. Is that correct? I'm still thinking.
So this is, I'll rewrite the formula. So f inverse prime of x is 1 over f prime of f inverse of x. So not log prime downstairs, but f prime is the derivative of e to the x, right?
Oh. I'm still getting confused.
Confused by the f's in the formula, or what?
Yeah. Because we're using f instead of f inverse.
Yes, right. Yeah, so yeah, the first one, the outside in the formula, is f and indeed not f inverse, right?
So I believe that we are going to have 1 over e to the power of log x.
Yeah. Good. And we have a nice way to write e to the log x. What is that equal to?
Is that 1?
No.
No, that is x.
It is x. Good. Okay. So now we have another extremely important result. The derivative of the log function is 1 over x. And now you see why I refuse to write log for the base 10 log, because some heretics in high school classes like to insist that when you write log with no base, it means log base 10. But if you do that, the derivative ddx of log base 10 of x is really ugly. It's log base 10 of x over log base e of 10. So this formula looks fucking ugly. Why should the derivative of the log function be the same function divided by this weird looking constant, which happens to involve e? It's really ugly, and I don't like it. However, if you insist that whenever you write the log with no base, it's log base e, then this proof that we've just done shows that the derivative of log is just 1 over x. Oh wait, sorry. Why did I do... Sorry, that formula I just wrote is not right at all. Why did I write log x? I meant 1 over x, but then times the change of base thing you would need. This is... Where am I getting this from? This is the same as log of x, log base e of x, over log base e of 10. Sorry, I don't know why I'm fucking this up. Yes. So the log base 10 derivative is 1 over x times 1 over log base e of 10. There we go. Sorry, the other thing was wrong. But my complaint still goes through. If you think that log base 10 is somehow a natural thing to write, then you are forced to memorize that when you take the derivative of your base 10 log, that derivative is 1 over x times 1 over log base e of 10. So you would say, why does this weird number show up when I differentiate my log? And the answer is because you were being silly by writing log base 10 all along. You should have not written log base 10, and you should have defined your log to be base e. Because if you do that, then the derivative is just 1 over x with no stupid factor. Anyway, that's my rant. So that's why all logs should be base e by decree, because the derivative is very pretty. Okay. I think there's one more exercise if you have time, but thoughts on this?
I have no thoughts or questions.
Okay, good. All right, this is what you just said. Yeah, 1 over e to the log x is 1 over x. Good. All right. All right, last one for today. So we're slowly extending our proof of the power rule to more and more powers, right? So we proved it for positive integers, we proved it for negative integers. Now we're going to prove it for these fractions, 1 over n. So x to the power 1 over n, by the way, is the same as writing the nth root of x. So how do you take the derivative of f of x equals x to the 1 over n? Well, the hint is that we should use the inverse function rule, right? Because the inverse function of x to the 1 over n is x to the power n. And we know how to differentiate that. So you have to be careful about which one is the f and which is the f inverse here. Using the inverse function rule applied to this thing, I will ask you, what is f prime of x for this function defined here? X to the 1 over n. What should I do?
So this is going to be 1 over, let me think.
Well, first let's do the easy step. So what's the derivative of...
My power supply fell off the table. I need a sec.
Okay.
That's why there was a pause. But my laptop was busy choking itself.
Don't die, laptop. You have so much to live for.
Isn't this lovely?
Yes.
So we have that the derivative of x to the n is going... Okay, let's think. Well, it's going to be nx to the power of n minus 1.
Good. Okay, so now if we're using our rule, I'm going to rewrite the inverse function rule, but I'm going to replace all the f's and f inverses, right? Because in this problem, I've intentionally swapped the roles of f and f inverse to see whether we understand the formula. So if we take the inverse function rule and just swap everywhere f with f inverse, then we get f prime of x is 1 over f inverse prime applied to f of x, right? Same thing, just replace the f's and f inverses. So we're going to use this formula now, where f inverse is x to the n, and you've just helpfully told me the derivative of f inverse is nx to the n minus 1. So now I just have to take everywhere an x appears in this formula and replace it with an f of x, because that's what this formula tells me to do. It says evaluate that at f of x. So I'll write that and then ask you to simplify it. So here is n times the quantity f of x raised to the power n minus 1. Alright, what do I do next?
F of x equals n to the power of 1 over n.
Good.
So thinking...
Power to a power, bro.
So this is going to be... Is this going to be x to the negative 1?
Well, let's see. So power to a power means multiply them. So what's 1 over n times the quantity n minus 1?
I believe that that is n minus 1 over n. Or am I thinking wrong?
Yeah, n minus 1 over n, which we can write as, split this into two terms, 1 minus 1 over n, right? Good. Or we should, it's the same as n over n minus 1 over n, right? Which is 1 minus 1 over n. Happy with this?
So this is going to be x to the power of 1 minus 1 over n.
Good, okay. Now for our last step, since this is in the denominator, we can simply put it in the numerator and flip the sign of the exponent, right? So if I flip the sign, this minus becomes a plus, the plus in front of the 1 becomes a minus, and I get 1 over n x to the power 1 over n minus 1. And lo and behold, that's what we would have guessed by naively applying the power rule to this function, right? You would have told me, aha, x to the 1 over n. Well, you should pull down a 1 over n and then subtract 1, which would give you a 1 over n minus 1 in the exponent. We haven't proved that before, so we couldn't just make that argument, but now that we have the inverse function rule, we can prove it, and indeed, it is exactly what you would get from doing that procedure. This thing. Good, so for those keeping score, we have now proven the power rule for positive and negative integers and functions or fractions of the form 1 over n. So almost all real numbers. We just still have rationals and reals. Yes, and that is the last thing, so I'll just show you the solution again. Yes, as you say, differentiate x to the n to get nx to the n minus 1. Pop that downstairs, replace the x with an f of x, which is x to the 1 over n. Power to a power means multiply. 1 over n times 1 is 1 over n. 1 over n times minus n is 1. And then we flipped that from the numerator to the denominator, which reversed the signs in front of the things I just said. So 1 over n minus 1, which is what we would have expected from the power rule. Okay. Lots of stuff today, but I think you are slowly getting to the point where taking derivatives is becoming more automatic. Other thoughts or concerns, comments on the big picture?
I'm feeling more confident with derivatives than I was with limits.
Good.
Probably,
Wait, sorry, what do you say? Probably because what?
or at least like halfway through limits.
Yeah, I think many people feel that way because limits are kind of... I like to think of it as a programming analogy. Like if you start by learning machine code or assembly, you learn like the very low-level bit fucking type of programming. That's like limits. You have to fuck around with epsilon and deltas, and it's a lot of work. Once you've built up a lot of like low-level C code, then you have nice compiled functions that you can just call without fucking around with the bit code. That's like Python, which is like derivatives. So derivatives are like Python, and as you see, we can often do derivative calculations by just calling nice results like the chain rule or the inverse function rule without fucking around with epsilons and deltas. But that doesn't mean you should forget the epsilon and deltas, because whenever you need a new function or a new result or a new theorem that isn't implemented in your high-level language, you always have to go back down to the low-level language, the bit-fucking language like C or machine code, and prove it. So that's what we saw today. You have to go back and prove these things with epsilons and deltas. So anyway, yeah, so it makes sense that you are feeling more comfortable with derivatives, because I think they're kind of more intuitive and easier to work with. But I mean, you shouldn't become complacent and forget the epsilon delta technology is the point.
Lovely.
You mad bro. Okay, good. I will hang up before you get a chance to say goodbye in a normal way.
Wait, no.